All right. So before proving the Alon-Babai-Suzuki theorem, we're gonna change the topic a little bit, and we will talk about the Mobius inversion formula. So if you took the number theory course, you may have seen the following theorem, that if you have a function, let's say you have a function f from, okay, so let's say g of n, so n is an integer, or positive integer, let's say. G of n is defined by this, then you can obtain f from g by some formula, right? And here you use something like n over d and d divide n. So this is called the Mobius inversion formula in the number theory. Now I want to tell you more a general version of that works on a partially ordered set. So let me start with the partially ordered set. What is a partially ordered set? Okay, partial order. A partial order, right? So X, this is a partial order if it satisfies three properties, right? So X is less than or equal to X for all X, and then if X is less than or equal to Y and Y is less than or equal to X, then X is equal to Y, and it's transitive. X is less than or equal to Y, Y is less than or equal to G, then X is less than or equal to G. Then we say it's partial order. So for instance, the subsets, right? So subsets of some set U and then set containment. This is partial order, right? And now we will define the Mobius function on the partial order as follows. Okay. We define mu s comma t for st in P. So mu st is 1 if s is equal to t, and 0 if s is not less than or equal to t. And what if s is less than or equal to, if s is not equal to t but s is strictly less than t? How do we define it? We define it as minus sum of mu as, let's say, u, where u is strictly less than t, and at least u, at least s, right? Right. So the whole purpose, so this is to make sure that whenever we sum up all, so for all s and t, if we sum this thing, then it's 1 or 0. So if s is equal to t, then it's 1 because you are only adding one element, and 0 if s is strictly less than t. This is the whole purpose. And so, by the way, this is definition. It's a recursive definition, right? So I know what mu of ss because it's 1, and then right, so you have a, let's say 1 2. So let me give an example, like 1 3 2 3 and 1 2 4, right, and 1 2 3 4, right. If my post set, my partially ordered set consists of these 4 members, then mu of 1 2 and 1 2 3 4, what is that? Well, this mu of 1 2 1 2 is 1, and then this is going to be -1, and then this is going to be 1, right? But actually it's quite easy to see what kind of, right? So if P is a partial order, okay, let's say P is a subset, okay, 2 to the x, then so mu of AB is what? -1 to the B minus A. Why? Because this is because if you sum up all the -1 to the B minus A, okay, let's say U minus A, and U is a subset of B and A. Oh, am I there all right? Yeah, that's right. If you look at this is gonna be what? The same as summing over all. Yeah, so K is from 0 to B minus A, right? And then -1 to the K, right? So I'm changing the variable. K is going to be U minus A. And how many subsets do we have which has the same value K? It's going to be B minus A, choose K, right? There's many ways to select subsets where U minus A has size K. And this is going to be 1 or 0 if B is equal to A or otherwise, right? If you remember the binomial theorem, this is exactly this. So this Mobius function, this function mu is called the Mobius function. For this partially ordered set P. For this partial order P. So why is this useful? So we are going to prove the following simple theorem. So let P be a partially ordered set, and then G of T is equal to okay, let F, G be functions defined on P, then G of let's say G of T is sum of F for all S less than or equal to T if and only if F of T is sum or over all S where you add G of S, and then you multiplied by Mobius function. So these two are equivalent. For all t in P, for all t in P. So that's the kind of Mobius inversion formula for the partially ordered set. So, and the proof is quite easy. Right, so for the forward direction, let's look at this formula, ST and GS, right? And I'm changing variables, and GS is sum of, let's say, u less than equal to s, f of u, right? Now, we change the order of summation, so u is less than equal to t, and right, I mean, first of all, let's do this. Yeah, it doesn't matter. U, yeah, so I'm choosing u and s at the same time, and then it's like st and f of u. If I fix u first, and then s is between u and t, and mu of st and fu, right? But fu is common, so this is. But by our definitions, this number is 1 if u is equal to t and 0 otherwise, right? So the only term that survives is when u is equal to t. So that means this is ft, all right? Yes. How about the converse? Right? Sum of fs. Right? I guess the converse is actually trivial. Imagine that I know that ft is mu st and mu s. No, sum of overall s, we are adding mu st and gs. So that means gt by the backward direction. No, by the forward direction. GT is, we are adding this again, and right now mu st again, and I'm getting this over here. Oh yeah, so let's not use same as mu ut, and then here you have mu let's see. Yeah, for all oh, okay. All right, let me try again. So we know this is true. So let's sum over all t f of s. Right. So that is f of s. Okay. Let's say this is u. Oh no. S and then f of s. So this is like u less than or equal to s, mu of us and g of u. So this is u less than or equal to s less than or equal to t, and mu of us gu, right? Now, what would be better? Instead of summing over s, I will sum over u, and then s is between, so there are two variables, but this is only one variable, and this is the variable that I'm summing, and mu us and gu, but u is common, and this sum is 1 if u is equal to t. So that's gu, right? Yeah, so we proved in both directions. So you can think of the Mobius-Inversion formula like the integration. I mean, the relation between the integral and the derivative, right? So if you have a function, if gx is this, then f of x is obtained by g, the derivative of g, right? Here you have a sum f of s, where s is less than or equal to t. Then f of t is sum of this guy, right? So this is analog. All right, so that's the simple proof for the Mobius-Inversion formula. All right, one of the students emailed me saying that there's some issue in my lecture about the Mobius-Inversion formula. There was one problem in the proof of the theorem. So here it is. So the claim is the sum of mu st is 1 if u is equal to t and 0 otherwise. This is what we used in the proof of the theorem. However, what we know is not this one. That was confused. I mean, I was confused. So what we know is, from the definition, what we know is something like this. SUT, the mu SU is 1 or 0 if S is equal to T or otherwise. So the difference is that S is the variable here that is running between U and T. So for U and T, and this is for S and T, right? So in this case, U is the variable that we are running. So a student asked me, how can we deduce this claim from these definitions? This is definition. Now let me show you the proof. It's the proof of the claim. And I'm going to do induction on let's say number of elements between S and between U and T. Let's say S is between U and T. All right. So if U is equal to T, then it's trivial. All right. Now let's consider the following sum. U1, U2, T, and S. So I'm running. So for S and T, let's consider the following. So we are running U1, U2. All right. Now there are two ways to look at it. Right. First, I choose U2 Okay, maybe I choose U1 first. And then sum over all U2. I add a U1, U2. And in this case, we know that this part is fixed, right? And then by definition, this sum is 1 if U1 is equal to T and 0 otherwise. So the only place where this sum is non-zero is when U1 is equal to T. So whole thing of this is equal to, so the only place where it survives is when U1 is T. So it's mu of T comma T, which is, so this is 1, right? I should say non-zero if and only if U1 is equal to T. So this whole sum is 1. But let's do the other way. If we sum over U2 and U1 is between U2 and S. Now, what we know is that if U2 is not T, and then if U2 is T, then right? So this is these are the cases for the case when U2 is not equal to T, and this is the sum. Now, by induction, so the thing is, now this part is fixed. And by induction, the number of elements between S and U2 is strictly less than number of elements between S and U1. So we can apply induction hypothesis. So this whole thing is non-zero if and only if S is equal to U2. Right? So that means the only place it gets non-zero is 1 plus S U1 T and mu U1 T. So therefore, S U1 T mu U1 T is 0. Right? We have assumed that actually U and T are different. Right? So this means, right? So I'm assuming that S and T are different. So this means mu of U1 T. And so what was the statement? Mu of S and T. Yeah, the variables are rotating. Yeah, I mean that's it, right? Yeah, that's what we want. All right. Now I'm gonna show you a cute lemma which we'll use later. I mean the next section. So here's a lemma. Let PQ be two partially ordered sets. Right, now we have two sets, and let F be defined on PQ to, let's say, some field, okay? Be a function. And G is also some function from P times Q to F. All right? And such that G of A1, A2 is defined as overall. So G of A1, A2 is defined as follows. So it's right. A1, A2. Okay, T1, T2. T1, T2 is defined as, so S1 is less than T1 and S2 is less than T2, and I'm adding all the S1 and S2. All right, so now we have two partial operators and sum of two things. Now here's the claim. Then overall sum yeah, I just need the correct formulation. So overall sum, yes, S2 less than T2. All right, so mu of S2 T2 and G of A1, no, not A1, T1 and S2. So I'm applying the Mobius inversion only on the second coordinate is equal to, for all S1 T1 and f of S1 and T2. So this is kind of slight generalization of the Mobius inversion formula. Right, for instance, if Q is trivial one, if Q only has single elements, then no, not the Q. If P has only single element, then this is same as the one direction of the Mobius inversion formula. All right, so it's also again an easy exercise. All right, so why? Why is this true? Well, let's see. Let's look at the left-hand side. All right. And by the definition of G, so this is okay. Now I don't want to use S1, no, S1, S2. Let's say U1 is less than or equal to T1, and then U2 is less than or equal to S2, and f of S1, no, U1, U2. All right, and then now I will change the order of summations. So U1, T1 is outside, and then S2, U2. Okay, S2, T2, and then U1, T. Oh no, not U1, T1. U2, S2. Yeah, so it's okay. Let's change the order. So I do the U2 first, and then so U2 is less than T2, and then S2 is between U2 and T2, right? So this is the variable, this is the variable, this is the variable, and then we have a mu of S2 T2 and f of U1 U2. All right, and now it's okay to make this sum first, right? And this sum is 1 if U2 is equal to T2 and 0 otherwise. So I can assume that U2 is equal to T2. So U1 is less than T1, and then u2 is equal to t2. So what we have is f u1 t2. Yeah, so that's it. All right. Yeah, so this is a simple computations, and in the next proof we're gonna use this to prove the one lemma which we didn't prove yet, the one theorem, the Alomba-Suzuki theorem.